Hello everyone and welcome to Big Orange Biology. I am Mr. Jennings and today we're going to do things a little bit different. So up until this point, most of the videos we have been working on have been either me in front of the camera or doing some, PowerPoints over a screen. Let's actually do some practice problems. So today in Big Orange Biology, we're going to talk about tenacity, specifically water potential. Now, water potential is typically one of the more confusing aspects for a student because we're taking something you've learned as a qualitative aspect, like tenacity, which is the idea of like hypotonic, hypertonic, and isotonic, and we're putting quantities associated with those. So we're actually telling you, hey, while this solution is hypotonic, it's really hypotonic because of this numbers. That in and of itself is not too bad. The problem is we're dealing with negatives. And while at this point in your high school career, you're probably familiar with how to work with a negative numbers in your problem, negatives really kind of mess with the mind a little bit. Kids get a little confused. Don't know why. I was one of them as a student. When I took AP Bio, this kind of got me confused at times. And even now, I still have to pause and think for a second. So don't feel bad if you have to do that. We're going to try to mitigate that and walk through some of these problems. So again, today we're going to talk about water potential. So I'm Mr. Jennings and class is in session. Alright, so we are looking at water potential problems. Now what that means for us is we need to be able to actually do these on your own. So at this point you have been assigned a series of practice problems. They may or may not include these at the time of this recording. I have not finalized the practice problems list. I have dozens of these out there. But these are some practice problems I have in the bank. So you may see one or two of these. Ideally you're going to see practice problems similar to this. So the actual math for this is not that challenging. The equations we primarily deal with are as followed. And go ahead and make up another one here. Today we're mainly going to deal with those two equations. So before we really get going, I want you at this moment to attempt these. There's only 3 problems in this video today. To attempt these 3 problems before I show you how to do them. It might be in your best interest to at least see how you can do at this moment. So I would like for you to pause the video, look at this, write it down, kind of make sense of it. See, doing the math is one thing. Knowing how to handle a word problem is the other. So at this moment, pause. Okay, we're back from the break here. So hopefully you did pause. If not, that sounded really awkward for you. And shame on you. Okay, not really. But let's say you didn't pause. You just didn't know what to do. So let's talk about how we approach this. So like I mentioned earlier, solute potential and water potential problems are in of themselves fairly easy equations. It's how to use those equations and understanding the concepts behind it that trouble most students. So the question today reads, the value of water potential in a root tissue is set at negative 3.3 bars. If you take the root tissue and place it in a 0.1 molar solution of sucrose at 20 degrees Celsius in an open beaker, what is the water potential of the solution, and in which direction would the net flow of the water be? So there's a little bit to unpack here. So let's actually walk through this problem and understand what the heck I'm looking at. So first off, we got the water potential. We are given a water potential here of the root. So at this point, we're going to signify this with a capital R-O-O-T. We're going to call this root. I am root here. So we're going to call this root, and it's negative 3.3 bars. For some reason I want to get that decimal too early. So we know the solute potential of the root. So we're going to go ahead and write out our given table. This is something my chemistry and physics teacher always taught me. It may work for you. So when I'm working with a bunch of equations, I always write out a given table. So the first thing is I got the water potential of a root at negative 3.3. That's the first thing I see. If you take a root tissue and place it in a solution, 1.1 molar solution of sucrose. Alright, so already here I got a concentration. And that is 0.1 molar, and it's specifically sucrose. Now that's going to matter here in a moment. We'll tell you why. And we got a temperature. Hey, we got a temperature. That is 20 degrees Celsius. That's going to be a little bit of a problem, but we'll fix that. Now, we have a lot of things going on here, but let's actually see what else we got. So these are the numbers that were given to us. Let's see what else is in the text. So let's look at the text here. It tells us we're looking at a root tissue. So also I like to draw pictures with this, so I got myself the nice little beaker. You don't have to go into super detail. I'm not. So I got a beaker here, some liquid of various types, sucrose solution. In there, I'm going to put my root. And just because I am not going to go complex, I'm going to draw a little square. I'm basic that way. So we have our root. It's in the middle of the solution. We know the root is negative 3.3 bars. All right, so hey, we got that going for us. The question's asking us, what is the solution's water potential? And knowing then, can we figure out which direction water is going? So we're trying to figure out the actual solution's water potential. So let's figure that out. We don't know anything about this being in equilibrium, so we can't make assumptions. But we do know this. That one pretty much doesn't give us anything, but we do know the solution. So we know it's a sucrose solution. It's got a concentration of 0.1 molar. Its temperature is that. Let's see what the equation is. So we're going to need to do the water potential of the solution. SOLN is abbreviation for solution. I learned that in AP Chem, and I never stopped using it. I recommend doing it. Saves you a lot of trouble. So we got this here, and we need to go in and figure out a bunch of little things. So I'm writing it out here just so I have this. It's for formality's sake. Not every time you have to do this. So we know some things. First off, we see this phrase here, open beaker. When you see open beaker tells you the pressure potential for solution, because we're looking at an open beaker means there's no pressure being exerted outside of atmospheric. So we're going to assume it's a big old 0. 0 bars, if you want to put a unit on that, that is redundant, but hey, whatever. So we know automatically this one is going to be 0. Hey, we already got halfway through the problem. Now we need to figure out the solute potential. This bad boy. And that's when we use this equation. Negative ICR. Now we do have a lot of this information. First off, while we don't have it in front of us, R is represented by 0.0831. I totally did not have to look that up. I actually do remember this. And it is liters bar divided by mole. That's the unit. This here is a constant. Constants are used a lot in equations like this, especially in chemistry and physics, to help clean up the math. They play a very vital role. They're like a conversion factor, but they help clean up the units, make things work nice. So let's look here and let's walk through it. So you're going to go, hey, Mr. Jennings, we don't know what I is. That's why we're going to come back up here. So the fact it tells us is sucrose. Remember, I is telling us it is the ionization constant. And for most purposes, the ionization constant is, I got lost track there, the ionization constant is either 1 or 2. If it's 1, it's because it is a covalent compound. If it's 2, it's ionic. As you recall, sugar, like sucrose, is strictly covalent. And such, that is going to be a 1. So I equals what? Board there on the screen. So I want to fill this in real quick. It's pretty easy now. So we're going to drop that off. We know it's going to be negative 1 times concentration, which we know is 0.1, R, which is this lovely constant here. This, by the way, is derived from gas laws. If you're wondering if you've had chemistry, hey, this looks kind of familiar. Yeah, it ties into gas laws. And then there's T. We got a problem. Our R is presented to us in kelvins. Our temperature is presented to us in Celsius. So we got to convert that. That is an easy conversion. Anytime you're going from Celsius to Kelvin, you just add 273 to it, and that gives you your temperature in Kelvin. Just don't forget, Kelvin does not use degrees. This here will be provided to you on the formula sheet. So I'm going to put that negative, not negative, 293. If it was negative, that would be impossible. All right. Now you're going to go, Mr. Jennings, I know my units, I know how conversion factor works, what do I do here? Well, molarity is actually moles per liter, so in doing so, the molarity cancels off the liters in the mole, the kelvins cancel, leaving only bars behind. That's how we know you did this correct. Now, as you simplify all this, you should find that the answer is negative 2.43 bars. I had to check my math here, that's why you got that awkward pause, if it seemed awkward after post. So negative 2.43 bars. So let's actually answer the question now. So we know now the solute potential, the water potential of the solution is negative 2.43 bars. That means that goes right here. Now the way water works is water will go towards where the more negative number is. Because that greater negative number means there's more solute. So negative 3.3 is a greater number, meaning water will rush into the root. So the answer to the question, what direction will the next flow of the water be? So let's put a box right in there. So the first thing you're going to do is make sure you box your numbers, and the answer to the question is it will flow into... Now that one's fairly easy. Let's take that up to the next level and switch it up. Let's see what happens when we change the solute potential. This one's actually not too big of a difference. So as I said before, let's pause here for a moment and see if you answered. Alright, welcome back here. So we are now going to go into what happens when the ionization constant changes and see what's the big difference. I'm not going to go through the big elaborate setup of the previous question because this is merely for perspective. So we know this. It's the same situation as before. So we got ourselves a root of negative 3.3 bars, and it's in a solution. We don't know the exact solute potential of the solution, so we're trying to figure out what is the solute potential of the solution. We are given the information. It's the same open beaker, so we can continue the information from before. That the water potential of the solution is going to be equal to the solute potential of salt. So we're just going to go ahead and go straight to the equation as I used before, negative I CRT. Now, a lot of this information is still the same, so our given table is largely the same, except small differences. So C is still 0.1 molar. Difference is it's salt. R is still 0.0831 liters bar per mole K. Again, same as before. Temperature, it's 20 degrees Celsius. Let's go ahead and convert that back over to 293 Kelvin. So we can see that. And now the I. I is different. So as I mentioned before, pull this back over here. I is either 1 or 2. If it's co-ionic, it's 2. Salt in this question, sodium chloride, is strictly 2. So you would just go to the same equation you did earlier. I'll put it over here. Negative 2 times 0.1 times 0.0831 liter bar mole K times 293 Kelvin. Units clean up rather nicely. And you could do this whole thing here again, or you can just go ahead and go right straight to the answer. You can go right straight to the answer because, hey, you may have realized this is the same number as before, just multiply by 2. Now, due to some weird rounding at the previous one, you should find out, though, that is actually negative 4.84 bars. The reason it's not 6 is because, again, rounding. There's some rounding rules going on here. So, hey, we're looking at this. Now we got a situation where the solution outside of the cell is more negative than inside. That means water will rush. So to answer the question, let's go ahead and label that. The question then goes, hey, what direction it's going to go? It's going to rush. Water leaves cell. So doing these after you do them first time, not too bad. Now I know we're kind of going here on some time. Let's actually go in and do let's do a more complicated problem. So you see the background there is still going. So what happens if you want to do a problem that is a little bit more complicated? You have to think it out. So this one's one of the more complicated problems. So at 20 degrees Celsius, a cell containing 0.6 molar glucose is in equilibrium with its surrounding solution, containing a 0.5 molar glucose in an open container. What's the cell's pressure potential? This one's tricky because it's asking you to do something that we don't normally view. So we're going to assume first off this is a plant cell. Despite being in an open container, the cells themselves have their own pressure potential, by the way. It's usually given to you, or it's assumed. In this case, we're going to solve for it. So let's look and see what we need for pressure potential by looking at the original equation that we have here. So we have that equation. Now you're going to go, Mr. Jennings, okay, we got some stuff here, but nothing really relevant. So what are we going to do? Well, you need to do this a couple times here. See, the key word is the cell's in equilibrium. That means it's at balance. That means the water potential of the cell is equal to the water potential of the solution. So what we need to do is first calculate the solution water potential of the solution. Second, we need to calculate the solute potential of the cell. And third, we have to then, solve for pressure potential. I'm hoping, by the way, when I edit this, the video will be a little bit shorter. At the time, I have no idea. So this is a simple order of operations. You're going to go, Mr. Jennings, this is crazy. And it's really not too bad yet. So let's go into it and elaborate on what the heck you're looking at here. So first off, let's do the thing as I mentioned before. The reason why you want to do the solute potential of the solution, the water potential of the solution, is because, again, water potential of the cell equals that. That means if we convert these to cells, we know that the pressure potential of the cell, and we're going to rearrange this equation. I'm just going to move things around. It's equal to the solute potential of the solution minus this, water potential of the solution minus the solute potential of the cell. Because the water potential of the solution is the same as the water potential of the cell. I just plug that in here and I rearrange it to solve for pressure, which is what the equation is calling for. So I need to get this of the solution. Now, solution is the same setup as before. This is a more complicated problem just for the fact that we are dealing with two equations here. So what I'm going to do is take what I got from the question. The question reads, hey, at 20 degrees Celsius, a cell containing 0.6 molar soup glucose, okay, so I got my givens going here, that the temperature, all I got really from this is temperature. We're looking at 20 degrees Celsius, which is again, add that 273, and that gives us that 293 Kelvin again. That shows up a lot. Now, the cell containing 6 molar glucose is not given to me for this problem. It's actually for something else. Now, this is a big deal. Surrounding solution contains 0.5 molar glucose. It tells me the concentration of the solution is 0.5 molar. And it's another thing about being an open container. That means its pressure potential is at negligible 0 again. So, hey, we got a little bit less work for us. We also know the temperature. We know the R. That's a given as well. It's always a constant. I'm going to omit the units. I don't want y'all to do that, so I'll do it myself. And you're going to go, Mr. James, what's the I? Again, we're looking at glucose and sucrose and all that, so it's still the 1. We're going to go ahead and quickly calculate that. So I went ahead and filled out the equation real quick here. So when you do that, you're going to get this lovely equation. Now, this equation that we see here is, again, all the information that's given to us in the word problem. And when you simplify it down, you're going to find that it is negative 12.12. And again, this here is the water potential of the solution. So we're going to take that information, plug it all the way back up to here. So, hey, we kind of got part of the problem done. So negative 2.2 bars. Now let's talk about the second part, the solute potential of the cell. Given, now we're not going to go into too much here since the temperatures are the same. So temperature is still at 293 Kelvin. The C is 0.6. Don't worry about the pressure potential. R is still 0.0831 liters bar per mole K. And the ionization is still, solute potential of the cell is negative 1 times 6 molar, 0.0831 liter bar mole K. It's a little rhythm to saying that all the time. 293K, I ran out of room with it. So the units clean up and you should get negative 14.6 bars as the solute potential of the cell. Again, we're talking cell here. Just want to make sure we dictated that, I guess. So I'm going to plug that up here. And at this point, you simplify. And you should get 2.4. Now, this here is pretty mentally intensive. That's a lot going on. Let me zoom out just a little bit so you can get a better picture. I'm sure your page looks just as crazy. This one is a challenging question. Now, it's not impossible, nowhere near that. It's relatively just taking what you know, and you have to make this jump here. The biggest thing is this inequilibrium topic. So anytime you see that inequilibrium, it just means the pressure potential of water potential of one side equals the water potential of the other. But every cell's a little different. Even a cell's technically a closed container, so that's why I can have a different pressure potential. So you got to basically figure out what is the number that's making this cell, the solute potential of the cell, which is different from the outside, obviously, because it's 0.6 and that one's 0.5. What is this factor here, in this case was the pressure potential, making it different? Basically, what was causing the difference between solute potentials to come up to where they're still the same as the water potentials of the cell and the solution are still the same? And that's all this goes for. Now you're going to go, Mr. Jennings, what is this all for? Well, one, the AP exam likes to do this, and also labs are really good to know it. This concept actually is very important to understanding how medicine and other IV treatments work. Understanding that saltier things tend to pull things through, more solute tends to pull. That's common sense, but this actually gives us a quantification for it and gives us extra evidence to support our claims that we can tie into our reasoning. So you've always had claim and reasoning, now you actually have a little bit more evidence other than physical or identifiable things like the cells swollen or cells shriveled. Talking about turgor and stuff. This one actually gives you numbers. All right. Thank you for watching. I know this has been an extended video. I don't know how much this will actually clean up in editing. At this time, I have like 24, almost 25 minutes. But thank you for watching. I know this is rather large. First off, they are math problems. Practice on these is what makes you better at it, and just keep working on it. Don't get too upset or too distraught because you get confused. That's normal. The thing is, you just need to think about the greater the negative number is, the more likely water is going to go towards it. That takes some getting used to. It's not an intuitive process. But thank you for watching. I hope you've learned something here today, and you can take it home and actually do something with it. So, again, thank you for watching. I'm Mr. Jennings. Hope you had a great day.